900K, I guess, do you have any idea what 900K means? I mean, 900K is about 600C. And when you cook stuff at home, you turn on your stove, okay? And then that 600C basically gives you kind of a red-orangish color, this kind of temperature. So it's very high temperature. Okay? And the sample actually, it's glowing orange color you can see in the vacuum chamber. But it's actually stable, so you do not destroy it. Anyway, so 5 is magical, second, and 6 is unstable, so on and so forth. Actually, what you see here is just the periodic variations I mentioned, but this is much bigger effect. The oscillation is huge. Okay, and what affects the temperature is the difference, the energy difference. So we just calculate the energy difference between this system and this system, and ask ourselves: is this system has lower energy, or that one has higher energy? Okay. And then you can do that computation. And so we actually measured that too. So this is energy different from experiment. And this is energy different from first principles calculations. So in first principle calculations, you see the oscillations here. But you can see 5-layer now positive energy difference. That means this guy is more stable. That one is less stable. And therefore the system is stable. So even though the energy difference is very small, it amplifies into a big effect. And one thing I want to mention, though, is that for some years, people have been arguing or have been questioning because that is, these physical property variations, are they all in phase? Not. So the answer is actually not. It depends on which property you measure. So I just want to demonstrate here that the work function variation here, I shown here this downward cusp here and downward cusp here, as I mentioned earlier. And this is not the same place where the film is more stable. So this actually, you can theoretically prove that the phase difference is 1/4 of a period. So there should be 1 layer offset. The place where the work function is lowest, the next layer is actually the most stable. So there's phase difference. And by the way, all this can be derived theoretically. Okay? You can look on my application. So it's not hard. You just go through this and you can prove all this stuff. Sometimes we use analytic computation. Other times we just do first principles, do numerical stuff. But this is actually this particular issue of the phase shift is actually divided analytically. So we have done that. Okay, so now next I'm going to mention electron phonon coupling. This may be a bit not so familiar to everybody. So phonons are just quantized lattice vibrations. And so electrons go through the system can be scattered off by phonons because the lattice vibrates, so it kind of disrupts the crystal potential. The electron can be scattered. And that coupling strength is called electron phonon coupling strength. Okay. And so in photon measurement, how do we measure that strength? That's the issue. The easy thing to do is that we do photon measurement spectroscopy looking at one peak. And we can measure the peak width. The width has something to do with the lifetime. Okay? So the width is delta E, and it's related to a certain principle with its lifetime. So when we raise the temperature of the sample, we have more phonons, more lattice vibrations, more phonons. More phonons, more electrons, phonons scattered. And more scattering, the electron lifetime gets shorter, and that means its energy width gets bigger. Right? So it's very simple measurements. We just measure the width as a function of temperature to see how quickly it goes up. So this width as a function of temperature for the different ones picked here. And you can see they have different slopes. The different slopes meaning what? Meaning that the coupling strength depends on the particular Coulomb state and particular energy. And so here's the Coulomb energy diagram. And here's the lambda, or we call the electron phonon coupling strength. And for the different Coulomb states as a function of thickness. And here's the experiment. And you see the periodic variations. And here's the calculation. Do you know who did the calculation? I did the calculation because all I did was, I said, wow, this looks very interesting about what I'm going to do. So I pick up a textbook. The textbook is, of course, filled with formulas. Okay? They're all too complicated. And I just decided to plug in the numbers and do the calculation. calculation, and it comes out that way. So I learned a very valuable lesson. I was a student at this institute. I was very good at memorizing all the formulas. Also, I hated that because I said all these formulas are totally useless because most of them you never use them again. And the other thing is you don't even believe they are right or not if somebody arrived at it, right? But I learned a very good lesson that actually these formulas are in fact correct and useful. So don't be frustrated when you see all those special functions and stuff like that. You may think you never use them, but they are actually quite useful. Okay, switch gear, talk a little bit of a different system, not just silver on iron. Okay, we have done other systems. And one system is lead on silicon 111. We are interested in lead because it's a superconductor. Now the electron-phonon coupling has something with superconductivity. It's strong. As you go back to the previous slide, you can see the trend is that when we go to smaller thicknesses, the electron-phonon coupling strength goes up. And so we came to the idea that maybe we will have a better superconductor when the film thickness is actually smaller. But of course, that's the wrong place to look for superconductivity. So I proposed that we should be looking at lead. And unfortunately, I just talked about it. We never got a student to do it. And somebody else in the audience while I was talking was looking at it. And so they actually did give measurements. But anyway, in this case, lead on silicon 111 also has periodic oscillations. And the oscillation period is 2.2 atomic layers. But 2.2 is not 2. So it's almost bilayer oscillation, but there's an offset. So again, there's a beating pattern. So every 9 layers actually offset by 1 layer. So you see a beating pattern, 9 layers. I just want to demonstrate the beating pattern you can actually see directly. So in this case, we performed X-ray measurements using a facility in APS. And I won't bore you with the details. You'll say we have done all these different films. So we start out with an 11 atomic layer film. And then we use X-ray to determine the film's thickness distribution. We find the film thickness is mostly 11, but with a look at 10 and 12, okay, the film is unstable at 11, so we cannot make uniform. But what happens after we raise the temperature, then you can see this unstable thickness goes away and the system bifurcates to 12 and 14 is more stable. And you keep on raising the temperature, and you can see the distribution gets wider and wider, and eventually the film becomes very thick, very, very rough, with all kinds of different thicknesses. But interesting though, you kind of follow the background, you can see there's even up and down oscillations, 2-layer oscillations, even odd oscillations. And then furthermore, there's a crossover. As after 9 layers, even odd becomes odd even, exactly what the theory predicts. So you can see even odd oscillations. And every 9 layers switches a phase. I think the battery is kind of counterbalance, right? But so if you cannot hear me, so just let me know. Wow, this guy is slow. Some of these figures are very large files, so it may take a bit. There we go. Okay, anyway, from that data, we can actually extract out the oscillatory part. So let's form an experiment from the oscillatory part. And you can clearly see this bilayer oscillation plus the plus the beating pattern. So that comes out very well. So I just want to demonstrate that. Okay, anyway, then somebody else went ahead and measured the superconducting transition temperature in these films. And indeed, they find that the superconducting transition temperature, TC, has this even odd oscillation. So 22 layers, 23 layers, 24, 25. So you can see that behavior. And then let me see how am I doing this time. Let me just say we actually also collaborate with a group where they also did this superconducting transition temperature measurements. And we actually discovered pseudo gap, was kind of curious. Okay, so let me just show you the idea. Okay, so here is the lead film, 19 layers, and then we do STM, and you see the Cornwell states. Okay, you see these discrete states, and in very good agreement with theory. But now looking at near the Fermi level, and you look at low temperatures, you see this standard Dyne's line shape, okay, with a superconducting gap there. And the nice thing is when you go to higher temperatures, you still got like a little dip, even though this is way above the superconducting temperature. It looks like we got super gap. Kind of the data actually look kind of like high TC stuff. So for a while we were very excited while we discovered the high TC behavior in lead, which is not known to be high TC. So that was very positive. But then we then went on, did more measurements, and in fact this is just the how many different thicknesses, and then again I have this mentality that is everything can be calculated. So I actually personally did the calculation, the thin lines on calculations. You can see they agree very well. And then the important thing about looking at the Fermi level right here, the pseudo gap. And then so here is the experiment. You can see the pseudo gap. 10K above superconducting transition temperature for different thicknesses. This is my calculation that comes out to be okay. So the physics is very simple. So this is electron phonon coupling. Okay, near the Fermi level, however, electrons cannot be effectively scattered by phonons because of reduced phase space. Because electrons get scattered by phonons, got to go somewhere. And near the Fermi level, there's not too many places for it to go. And therefore, the reduced the phase space gives you a slow gap. And when we put that in there, it comes out in the calculation. So that's just a side note, saying that again, there are probably students in here. Just encourage you that formulas in textbooks are wonderful. They actually work. I have not found a single formula which is not working. But of course, I only used a few so far, but they all work out okay. Okay, so I'll switch gears to talk a little bit about more recent stuff that we do. I'm just going to superficially. I won't go into great detail. The one thing is topological insulators, which I'm going to give a more detailed talk. I think on Thursday when I give it a signature. Yeah. So on Thursday, I'm going to give two talks. One on topological insulators, the other one on charge density waves. So I'm going to go through detail. But anyway, here the idea, I'm sure most people are topological insulator experts, right? You all know what it is. So anyway, the first thing when it came out, I was very puzzled. What is so topological about it? And then so every talk I went to, they all show a donut with a cup, with a handle, and then they say, well, these two belong to the same topological class. That I agree, fine, no problem. But after that, everything is just completely crazy. You just don't know what they're talking about. You don't see the connection between the donut and all the rest of the stuff. Okay? Very, very frustrating. And in fact, one time the guy actually came up with the names of the, and asked him, well, what is so topological about it? And he couldn't really give a very good answer. I guess topological sounds very exciting, so you get your paper published. And everybody notices it. So anyway, I'll give you a simple explanation of what's relevant to our work, which I'm going to talk more. Now there's a spin-orbit coupling effect. Okay. And so standard semiconductors look like this. You got valence band and conduction band. Here's a parity plus and minus. That's normal order. But when you increase the spin-orbit coupling, oftentimes, not oftentimes, sometimes the coupling is so strong the bands get inverted. So parity plus goes here. The conduction band has minus parity up here. Okay. So now you get this inverted region, which is topological insulator. Normal insulator, which is got a normal band ordering, and put them together side by side. And then remember, the electronic potential has to follow alphabetically from one to the other. And so you got this band edge has to go from here to here. The band edge go from here, got to go there. And so just imagine you follow along in real space crossing the interface. At some point, the two band edge must close and forming a metallic state. So the net consequence is that a topological insulator is an insulator in the bulk, but its surface is always conductive. It's always metallic. And it's that independent however you do it. You can use a file, you can do whatever. It's always metallic because that's the requirement of the geometry or topology. Now, of course, some people tend to say something fancier. They say it's protected by time reversal symmetry. Well, it's technically correct, but that's That's not a very intuitive way of saying, of course, you get your paper published. That's really what it is. So the important thing is that boundary, you have an interface state which is always metallic, and then the other thing is the spin overcoupling gives rise to spin polarization. So this guy is actually spin polarized. And so naturally you get spin current on the surface, which goes around, and a perpetual current, and of course you don't have that, because it doesn't have carry any real current. It has no dissipation, so it's just like, when you think about it, it's not so hard, okay? Just like you think about a hydrogen atom, you got an electron going around, you got a perpetual current there. Of course, I mean, this is probably fake, right? It's kind of like that. Not very useful. So anyway, and the other important thing is that then when you have this inverted situation, so this ordinary semiconductor insulator, the surface states, you could have surface states within band gap, but they look like this. But in the topological case, then because the inversion, one surface state has to go like this, the other has to go like that. They always span the band gap, so to satisfy the criterion that this guy is always metal, no matter how you do it. So that's the only way you do it. The surface state always span the band gap. That's the consequence. And, so we actually have looked at some of the topological systems. So antimony is a very simple one. So we do our usual thing. We just deposit one layer at a time and looking at topological surface states. And so here we see the valence band. Here we get home wall states just as before, beautiful. But here's the band gap. You can see the topological surface states, kind of like we talked before. So they are spin polarized. So this they form a Dirac cone right here. And so just like what theory predicts. In fact, again, we can do this calculation pretty nicely. And so one issue of question is of interest is what happens when you make this film very thin. Okay, the topological insulator is a 3D property, right? But what happens when you make it very thin? So something that does it still become, well, what happens, can you still call it topological insulator when it's thin enough? Well, that's a question. So we did a measurement. So just imagine here's a 20 layer. You have a surface state. She's vacuum and these are the layers. And you got a surface state near the surface. Now, if you go 4 layers, you got surface state here, you got surface state here. The top surface and bottom surface, they get so close. And you can see the wave function overlap. So they are no longer separated. So you have this kind of coupling. Now, the coupling basically gives you right kind of anti-crossing. So you got even order combinations. And so as a result of that, the surface state band is shown before. You should open up a band gap. People call it tunneling gap. There's really not so much tunneling to it. They say tunneling from one end to the other, you have a band gap. So here's the calculation. One layer, you got, well, one layer is not an insulator or anything. One layer is not a solid. And then 2 layers, you got to see the topological surface state with band gap. 3 layers got band gap. 4 layers got band gap. 5, 6, 8, and eventually it looks like a Dirac cone right here. So by 4 layers, it's almost like a bulk-like. So here's experiment. 4 layer and 20 layers is like a bulk. So here the topological surface states, topological surface states, and here the calculations. And then, well, you can see 1, 2, 3, 4 states, 1, 2, 3, 4. Well, the calculation is amazing. Okay, these guys can do amazing things. Okay, I'm sure they are theorists. You have my best respect. The wonderful things, it comes out wonderful. But it might be picky though to say, well, what about that kink? So on and so forth. Okay. Again, this has something with substrate. In the calculation, there's no substrate, so you put in substrate. That should be kink. Okay, here's the big block you can see. So, but the important thing though, at 20 layer you got Dirac cone, and 4 by layer is to see that guy. You blow it up, you can see the Dirac cone right there. Boy, where is the tunneling gap? There's no gap. And then you blow up the theory, you see a gap right there. So what's wrong with that? That has something with the substrate. Okay? Because tunneling happens only when the 2 surfaces degenerate, so they can couple. But with the substrate, the bottom surface is not the same as the top surface. So degeneracy is removed. You don't have that coupling anymore. Okay? And so in the calculation, then just ask, I forgot who did the calculation. It's one of my postdocs. Why did put hydrogen on the bottom surface? And sure enough, that removes that thing in theory, and it actually looks much better when you compare to experimental. So again, theory works. And we understand all this stuff. And so this is just one example of the issues we work on topological insulators. So now, what do we do next? Now everybody is moved beyond, that is the irrational metal, and there's the Majorana fermions, and there's the wire fermions. So we are doing wire fermions. So it's the same thing. Type 2 wire semi-metal. That is, you got fermions on top of the surface, bottom surface all got fermions. But when you make thin enough, they should couple. So that's something we are working on right now. And we're also working with Professor Ai-Wei Wu, using his STM technique to look at some of these issues. And another thing I want to mention is that something else we do, that is using synchrotron with a polarized synchrotron light. So the synchrotron light comes in typically linearly polarized. But you can do it, you can control it such that it becomes left or right circularly polarized. And that will then allow you to probe the spin configuration of the electron states. Topological surface states are spin polarized, so that becomes useful. So this is a 2 principal layer and this 12 principal layer of bismuth selenide silicate. This is a topological insulator, topological surface states. And so with the left circularly polarized light, you see one side gets illuminated, and use right circularly polarized light, and the other side gets illuminated. And using that technique, you can actually deduce spin polarization. But not so trivially, it actually turns out to be a very complicated process. I'm just simplifying it. And you do need to do a lot of calculations to extract the spin polarization. So that's something we are doing right now. And then, yeah. The experiment is not so difficult. You just need a polarized light source. Yeah, you need a circularly polarized light. Now in the synchrotron, most beamlines are actually not only linearly polarized, so you do need to pay special attention how to build a beamline to make circularly polarized light in a controllable manner. So that's actually one actual know-how. But it's very important. So the next beamline we are building at TBS, there will be that will be fully controlled elliptically polarized. We call it elliptically polarized light. That means you can change the polarization any which way you want. And the other thing we want to add is spin detector. So the light can excite a certain spin configuration, but also detect the electron spins directly. Actually, that's an interesting homework problem. How do you detect the spin of an electron? I'll let you think about it. Limits on the best. Ask him. Yeah. Okay, the other thing, we are also looking at the two-dimensional systems. So I talk about topological insulators, those are 3D systems. But there are also 2D topological insulators. That's basically saying the edge is a metallic edge. So you are insulating film, the edge is metallic, and you can do those things. And we hope to build a nano upper spin line so we can look at edge states. Hopefully in the future we can do that. And so you just need to give us money so we can do it. But by the way, he is a very powerful person. He controls all the money. Well, I won't bother you with all these details because sometimes some of this stuff is actually pretty complicated. It's very hard to explain. I'm trying to make it simple as possible, but I might be committing fraud because it's really too simple. So, anyway, I just talked about a few other things like graphene that we also have a look at. Graphene is very interesting. That you can see there's a Dirac column at the K point. So one layer is one Dirac column, 2 layers is 2 Dirac columns, 3 layers is CPU, and so on and so forth, just like a thin films. Okay, no problem. And then you can use left circularly polarized light and right circularly polarized light. You can limit 1/2 only. So here's a linear polarized light. Okay, you can see only one side. And then you can do experiment looking at the contour around here. You can here's experiment theory, and in fact, this is a direct mapping of the Berry phase. So Opus is a wonderful machine. You can do a lot of different things. And another thing we have been doing recently, which I'm going to talk about in detail on Thursday, that is titanium diselenide. It's a charge density wave compound. You can see 1 layer, 2, 3, 4, 5, 6 layers. at room temperature, this is the low temperature, there's band folding, and then CEW condition. Here's a calculation done by Mei Chao's group. Mei Chao, of course, you all know, is the vice president of India Silicon. And you can see one layer looks like this, 2 layers got form of state right there. You see the calculation, and 6 layers got all these active guys. So okay, again, theory works.
Thanks.
So this is not like in ancient time. Yes.
So it seems to me the 3 layer case, at least 300 Kelvin also have this some signature folding.
Yeah. Well, okay. I'll be honest with you. We do not completely understand everything. I think there's probably something missing in here. But the large features, the obvious features, they agree very well. There are small things. I must say, even so, we have been working on APUS for so many years. APUS process is not completely understood. We're still working on that. So APUS doesn't really, is a complete process things beyond the single particles stuff. Okay, so I'm going to summarize by saying that thin films are basic building blocks of devices that drive us to look at thin films. In fact, I started doing this in 1978. I started doing thin films. That's because my boss at IBM told me that thin films are the thing of the future, so we should be doing that. So we're still doing that. And we see quantized electronic structure in films. And so we see very different from the 3D case. We see discrete conducting channels. And so you can imagine you can even have metal you reduce thin enough. You can have a situation metal can turn into an insulator. All kinds of possibilities. And the most important point I want to make is the periodic table effect associated with thin films of 1D shell fitting. We have demonstrated that. And then by controlling the film thickness and the interface, we can actually hopefully achieve design electronic states. And one in particular example is the high thermal stability. Obviously, when you make the films as thin as like a few layers, like in devices, which inevitably you're going to get down to that limit. And thermal stability has got a big variations. I think I was giving a talk at PowerChip. Wow, okay. At some point, we probably had to worry about it. And then we are also looking at, it's very hard to explain all this stuff. So I didn't talk about Dirac, Majorano, and all that stuff in great detail. It's something very interesting. And actually, after this, what's the next name? Do you know? After Dirac and Weil, what else is this? Minchong? Anyway, we have achieved a pretty good understanding based on first principle in model results. And so the next hope is that we have this understanding. We hope to actually make that useful to devices. So with that, thank you.
Okay. I think that Dirac and Weil, Majorana's particles are actually from the high energy physics.
Yeah, well,
so actually, my conclusion is high energy physics has a very good future in the solid state physics. So you are welcome to come to join us.
Yeah,
so,
actually, I need to talk to my high energy colleagues to see what's the next name is going to be on the list.
Yes, don't ask me.
Yeah,
okay. Okay, so now it's open for question or comment. Or we have high energy people here. Maybe if you sometimes maybe you can mention a little bit about the free electron laser.
Yeah, free electron laser.
It's also very important direction for the light source.
Yeah. Well, I mean, so we use synchrotrons to generate light, but there's a different way of generating light. That is use a free electron laser. The free electron laser is a circular machine. We have a linear accelerator, very long, and it should beam into an angulator, which is a periodic magnetic structure. And if you do the beam correctly, then you get a coherent interaction between the electron beam and the magnetic structure. Then you get a coherent radiation coming out, which is actually laser. And the best use for that one is for femtosecond spectroscopy, time resolved measurements. Because that one you can get very short time pulses, on the order of tens of femtoseconds. So that would be very useful for looking at structural issues. For example, people now, one big application is that you have this biological molecule containing liquid droplet coming down, and you blasted with actually beam, and you see a diffraction pattern because the beam actually destroys the droplet with so much energy. But in that one shot, you get actually a diffraction pattern. And then you just throw in, say, a million droplets and collecting a million pictures. They all come down in random orientations. So with a million pictures, then you can figure out what's coming down there. Or just like I take a picture of you like this, and take another picture at a different angle. But I take a million pictures, I can figure out exactly how you look like in real space. Okay? So even though I see only one side of you for one shot, since I have a million shots, I can actually stitch them together using software, artificial intelligence, and figure out every little detail of you. And so that's. But when you talk about free electron laser, let me give you a simple explanation. You all use microwave optics, right? And that's almost like that's called laser. It's almost like a laser. So it's actually coherent conversion between electrical energy and radiation. So the microwave is extremely efficient. You plug in the wall, most of the energy goes in microwaves. Now you hope to have the same machine plugged into the wall. You get all the radiation come out in X-rays, but that's very hard. That's why in a multi-billion-dollar facility to do that conversion. So you're going for microwave, that's easy. For the X-ray, it's very hard. So that's why the LCOS I've shown the picture. And there's a gigantic machine that originally built for high energy physics, but now it's converted into a light source to produce light. Now Taiwan has an index, the short one, they should be able to do terahertz, which is a bit higher than microwave.
I think they are discussing, but not deciding.
I think it's kind of interesting to do it. It's like a big microwave oven. It's higher energy.
Okay. Yes, please.
A simple question that apparently it's a critical thickness from 2D to 3D states.
Yeah.
However, when you grow a very, very thin film, although it's ultra thin, but it's still 2D.
Yeah.
So how can you get this 1D shedding feeling?
Well, I mean, it's a gradually, right? I mean, the 1D is the Z direction that is building up along the Z direction. This is infinite, both in X and Y. So 1D refers to Z direction.
In the conventional crystal growth, like in the molecule in the taxi, right, the substrate temperature is usually higher. The argument that you need to have some thermal energy so that the particle can move around. But in your growth model, you actually go with a very low temperature, and I think it's very, very hard to control the thickness this way, right? Because the particle when it gets thick, and then so how do you control precise how much amount of atom deposit, and then you anneal it, and you can get a 1 layer, 2 layer, 3 layer. There's something very magical to me that you can actually do that.
Well, it's just you have to have a very stable vapor source. So you calibrate that thing. So like we did 1, 2, 3, 4 layers. That we have gone through a lot of calibration first because we just deposit a little bit until we hit 1 layer. We say, okay, we know the rate now, and then we check it 2 layers, 3 layers, and then so forth, and then get it all done. And the other way to do it is simply not try to do this thing so in the first place, simply just deposit small amount and go through the whole sequence, and then at some point you get the right amount. That's the one you take out. You have infinite time, right? Or you have a very patient students, which seems to be harder to find these days. Actually, the guy did that was a German, and he was the German attitude was he does things precisely. I think I learned a lot.
Okay, but did you try the meter read to see the oscillation?
You can also do the real oscillation, but in many cases, you have to have very stable source because your source.
No, the source came from Max from Germany, so I use that.
Well, no, the source we have is a home built source. He didn't bring anything, but it has to be very stable. So once you have demonstrated you know you can do real oscillation or do whatever. Once you demonstrate this is exactly right, then you should be able to produce day after day. That's a secret. Otherwise, every day you got to recalibrate the thing. There's no way to do it.
Okay, further question? Yes, please.
For the silver on this iron 100, it's exceptional thermal stability at this 5 monolayer. Must have something to do with this specific interaction of this specific to the interface between silver and iron. Can you say something about that?
Yeah, well, the calculation actually does have to put in the substrate in the calculation, so the substrate does play a role. Yeah, so when you do that, and you'll find 5-layer actually, just for that particular one, the energy difference between the bifurcated film and the original film, the energy difference is particularly large, so that one is more stable. And everything else is not so stable.
And this 5 monolayer is not stable, it's not very stable in other systems.
Well, the 5 layers depend on your substrate. You have a different substrate because you're going to change the phase shift. It will be different.
Maybe I can answer some fundamental question. Even in your formula, I think the first or third page, so you have the phi 1 and phi 2. This is the phase difference. I think maybe you can explain it to the.
Now the two phases, phi 1 and phi 2.
Maybe could you please show that for the students? Maybe it's not so simple like the quantized spinning wave. So they put some phase shift.
Well, you can do all those calculations, no problem. We're way back there. Very long. Very slow. We need better computers. I don't know, there's something offending here. Always make it very slow. I think it's probably got an equation object in there, which always makes it slow. No, this is my computer. It's actually
No, it's a old and a second pad.
Well, it's the top of the line.
At the time.
Yeah, that's a time. But mostly it's PowerPoint issue. I think the PowerPoint is very efficient. Yeah, okay, so here I guess Minchong's issue here is there's a condensation condition. So the formation of this discrete states is 2 times the k perpendicular in the thickness of the thing. This round-trip phase shift, geometrical round-trip phase shift, plus the 2 boundary phase shifts equal to 2 pi times n. That actually works. Okay? So it's not an ansatz or anything. That actually follows from quantum mechanics. And then so phi 1 and phi 2 does depend on the particular system. So you put a silver on iron, you get a particular phase shift. You put a silver on silicon, you get a different phase shift. So you could have a different stability curve.
Yeah, that is fine. So depending on the subject. Okay. Any further question? Okay. If no, I think we are very happy to have this talk. Thank you very much. So let's thank the speaker again.